we have moved to how are we going to solve the mathematical expressions. Again, I have rewrite these equations and becoming equations 1, and then we have the next equations. This is going to be equations 2, and we are going to make use of these two equations in solving the isentropic efficiency and also mass flow rate. There's another equations that I forgot in the previous video, which is this work output of your turbine. So it is denoted as W dot out, which is equal to M dot times with work out. So in this case, you were given 2 megawatt, which is equivalent to 2000 kilojoule per second. So this is also the third equations that we are going to make use in order to find your mass flow rate. Alright, so we are going to need to find our enthalpy at state 1, which is the inlet of the turbine, and also enthalpy at state 2, which is the outlet of the turbine. And if you have obviously we are going to need to read our property table, and if you forgot on how to read your property table, you might want to have a look back at this playlist where I have simplified the way we are going to read our property table into 3 parts. Okay. And so if you have your textbooks with you, you can go to Appendix 1 where we have property table charts in SI unit. So because of this is a water table, so we are going to refer to table A4, A5 or A6, right? So let me scroll through table A4, and then we have table A5. The difference with A4 and A5 is on the first column, where A5 you have a pressure column, while A4 you have the temperature column. Right, so moving next is your table A6, where you have pressure reading row and also temperature reading column. So we go back to our questions that we have over here. Obviously, for state 1, it was given pressure and temperature, and the property is in a state of steam, which is already in a gaseous form. Therefore, for state 1, we can read right straight away from table A6. So this one, in finding your H1, right? So we are going to read directly from table table A6, what will be your H1. So 3 megapascal and 400 degrees C. Scroll back to your property table and look for 3 megapascal row. And there you go. We have 3 megapascal row over here. And the temperature is actually 400 degrees C. So for 400 degrees C, you will read what is the value of your enthalpy from the third column. So again, 3 megapascal, 400 degrees C. So the value for your H1 is 3231.7. So we are going to write that down. Your H1 is equal to 3231.7 kilojoule per kilogram. Right? You are going to do the same step with state 2, where again you were given pressure and temperature. This can be read from table A6, whereby your H2 is equal to, using the same step that I did for state 1, you will get for your state 2. Is equivalent to 0.05 megapascal at 100 degrees C. The H will be 2682.4. Have the value of your H1 and also your H2, but please denote that because of this is an actual process, so your H2 is actually your H2A. So if I can sketch this in your TS diagram, right? So your turbine is experiencing between these two pressure lines, 3 megapascal and also 50 kilopascal, right? And then you have your from state 1 to 2, and this is actually your 2 actual. This is your 2 isentropic. Okay, so the one that were given to you for this value at the outlet it's actually owned by your actual value. So how are you going to find your T2S? So for uh, isentropic work, right? For isentropic work, your value of your S1 must be equal to your S2S. So if I were going to write it, it's going to be like this. S1 is equal to S2S. Okay, then what will be your H2S? So this is where we are going to find out using the value that we get from S1. A property table over here where we have 3 megapascal, and at 400 degrees C, we will need our entropy value, which sits at the 4th column over here. So 3 megapascal, 400 degrees C, the entropy value is 6.9235. Your S1 is equal to your S2S, which is equal to 6.9, again, 325 kilojoule per kilogram dot Kelvin. S1, which is equivalent to S2S, which is this is the value that we get over here. And you can see that your S2S lies in the 50 kilopascal pressure line. So this is where you are going to get, this is how you are going to get your H2S value. So please pay your attentions on this matter. So you are going to have your H2S read from table A6 where the value is 50 kilopascal. So let's have a look at your property table over here where we go back to 50 kilopascal or 0.05 megapascal, but we are not focusing on this 100 degrees C. We try to look at the value of S. So when you have a look at 0.05 megapascal, the value of S that you have is 7.5931, whereas the one that you are concerned with is 9325. Okay, so obviously what you have is somewhat around here, not on the gaseous phase. Okay, so this is quite tricky, but we are going to find what will be your H2S. Redraw, right, this TS diagram over here, because obviously it was in a mixture region. Okay, so the one that we are going to have is somewhat like this, and you have 2 working pressure. One is 3 megapascal and the other one is 50 kilopascal. And that from state 1 to this one, which is you are going to have S1 is equal to S2S, right? And this one is the 2 actual part. Okay, as you can see, we already resolved for this 2A, okay, where we already have our H2A over here. But because we wanted to find the isentropic efficiency, thus we will need your H2S. And we recap back your H2S at 50 kilopascal is in the range of mixture region. So obviously when it is in mixture region, you will need to find your quality of X using the equation from Y is equal to YF plus X YFG. So in this case, you are going to need your H2S, where you will make use of HF plus X HFG. And in order for you to find your X, you are going to make use of your S2S is equal to SF plus X SFG, where all this will read from table A5 at 50 kilopascal. So let's do this.